Hello and thank you for watching my video. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. On this video, we are covering CCNA CyberOps, and this is Chapter 4, Network Protocols and Services. Now, Chapter 4 is made out of 6 sections. Section 4.1, in there we will be talking about network protocols, like application layer protocols and transport layer protocols, network layer protocols, as well as data link layer protocols. It's like a kind of like a review of your CCNA routing and switching ICND 1. Then we move on to section 4.2. In there we talk about layer 2, like Ethernet, what happens in there, as well as layer 3 internet protocol for IPv4 as well as IPv6. Then we move on to connectivity verification. In there we'll be talking about pings, traceroute, and so on, as well as section 4.4. we move on to address resolution protocol, the benefits, and then some security concern with ARP, as well as IPv6, what do they use instead of ARP. We move on to section 4.5, the transport layer. In there we will be discussing layer 4, two protocols, reliable and best effort protocol in depth, the TCP and UDP. As well as we move on to section 4.6. In there we talk about application layer protocols more in depth, like DNS, DHCP, and HTTP. Lots of things to talk about, but if you have covered your CCNA routing and switching, it's kind of like a revision to what we learned or what we know already. Section 4.1, network protocols. Upon completion of this section, you should be able to explain how protocols enable network operations and explain the basic operations of data network communications. Section 4.1.1, network communication process. Now, views of networks. Network comes in all sizes. They can range from a single network consisting of only 2 computers connecting together to millions of devices connected together. Small home networks are usually set up by individuals that work from home, or a remote office that you need to connect to corporate network or other centralized resources. So small networks are set up by some individuals. They can contain just one PC, maybe connected to a router, a printer, and that's it. Then we have a small office or home office networks. These are peer-to-peer, kind of peer-to-peer networks. No computer will have a centralized control over other computers. Each computer will have a set of user accounts. To log on to any computers, you will have to have an account on that computer. So each computer that will be in the desk here, you have to have an account in there. If you want to log in, you need the username and password. If you want to log on to this, you need the username and password. So there's not going to be any centralized control over these computers. They are typically around 20 computers on the office, and all computers must be on the same subnet. So they will be on one same subnet. So there's no subnetting for you to worry about. There's no VLANs for you to worry about. They're all in same subnet. No control. Anybody. All the security is controlled by a single computer. Then we have a medium to large networks. Now we're talking about we have a servers. They control, for example, as a centralized control over other computers, kind of like we create a domain where these little computers here, they didn't trust anyone before. Now they trust a server, like Active Directory. For as long, this makes it easy to make changes because the changes are automatically made to all computers. Now, these domain users must provide a password or other credential each time they access a domain. But if they have a user accounts, then they can log on to any computer on their network. And these kind of networks, they can be thousands of computers. The computers can be on a different local networks. For example, we can have a different subnets here. We can have a subnet, different VLANs as well. And this type of network, we have to worry about the access control list, who's talking to who, and so on. And then we have the largest network, worldwide networks, which is the internet, which is the largest network in existence. In fact, the term internet means a network of networks. The internet is literally a connection of interconnected private and public networks. Client-server communications. All computers that are connected to a network and that participate directly in the network communications are classified as hosts. We call them hosts. Now, hosts are also called end devices. So end device. For example, this computer participates on the network. This one here sends and receives files on the network. We call them hosts. Doesn't matter if they are end clients or servers, they are still hosts. Much of the interaction between end devices is client and server traffic. For example, when you open a web browser on the client computer now and access a web server, this is a client to server communication. Now, what makes this a client? Well, whatever operating system you installed on it. So for example, you install Windows 7 or Windows 8 or Windows 10, for example, that makes it a client. For example, if we install Windows Server 2016 here, or 2012 or 2000, whatever, that makes it a server. So servers are simply computers that have specialized software. That software enables services to provide information to other end devices on the network. A server can be a single purpose. So for example, a server can have a web server only, or you can have in one server have all these. You can have a web server, you can have an email server, as well as you can have a file server. There's another type of network which is peer-to-peer. Peer-to-peer. That is not, we don't have a server on that network. We have just clients connecting to each other. Now, if we have, for example, in a peer-to-peer network, which is usually your home network, yeah, you have a computer connected to another computer like that. Now, in this type of network, this computer can become like what we talked earlier with the home networks or small office, home office network. This peer-to-peer network, this client can be a client, or it can become a server. So for example, if this computer says it has a folder, is sharing, and this computer is getting that folder, now that computer here is a server, and that host or end device here is a client because it's accessing it's accessing the folder. If this PC here, host, end device, whatever you want to call it, for example, has a printer, so that's our printer, and it's sharing the printer. Now this computer or host, when it's accessing that printer, this host becomes a client and this host becomes a server. So depending on the role, for example, you can become a server, you can be a server as well as you can be a client. That is on peer-to-peer network. On a client-server network, the client is always a client and the server is always a server. It's always going to ask its services. It's always going to give the services to the clients. Tracing the path when we need to connect to a website to read, for example, a social media or shop or do the banking, we seldom care about how our data is moving to the website or how the data is coming from a website to our network. But as a cybersecurity analyst, you have to make sure that you know exactly where the path the data is taking to leave your network and what path the data is taking to come to your network. So that should be your primary concern as well. For example, users, they don't really care about that. They don't really care how the data is getting to the destination, how the data is coming back from the destination. We have a tier 1 and tier 2 networks. For example, these type of networks, they connect with the internet exchange point to each other. They connect pretty much the internet. And we have big companies like a point of presence. These are big businesses. They connect directly to tier 2. And usually they have the device that connects on their building, they connect directly to the internet. So that tier 1, tier 2 connect together. And tier 3, for example, these are the providers like ISPs that communicate to us. Section 4.1.2, communication protocols. What is communication? Like we said earlier, the network can be as complex as the whole internet, millions of devices communicating with each other, or as just 2 devices communicating with each other. That's a network. For communication to occur, the devices must know how. You need to know how to communicate. For example, 3 elements that we need to get is the first element, we need to have a source. So who is the source of the communication? Then we have a destination. So where destination? There's always going to be the source and destination. And then the last element that we need to think about is the channel. So source, for example, host A is trying to communicate with host B. That host A is the source. The host B is always going to be a destination, source and destination. And then the media or the channel. Is it going to be using fiber optic? Are we going to be using, for example, wireless? Or are we going to be using copper medium? Those are the three elements that we need to know about the communication. We need to know how to communicate. We have a source, destination, and channel. Establishing the rules. Once we know how to communicate and we establish the three elements that we talked earlier, like for example, the source, destination, and the channel, then we need to establish rules. For example, we have to first think about message encoding. Encoding is the process of converting information into another acceptable form for transmission. These messages sent across the network are first converted into bits by the sending host. Each bit is encoded in sound, light waves or electrical impulses. Now, you need to know how to encode. So the source needs to encode something. For example, put the information as a light waves, and then the destination needs to understand how to decode these messages. Then we have to agree on message formatting and encapsulation. How are we going to format the message? So message is sent over a computer network, follows specific format rules for it to be delivered and processed. Just like we send a letter, we need to know, for example, say we send a letter. We need to follow the format. So we have the sender, for example, here, and then we have the destination here. So that's our two elements already. And the letter, the way it goes to the destination, that's the channel. So we need to format this, for example, so the routers on the path, they will be able to read the destination. Each computer message is encapsulated in specific frame format that they are called frames before it's sent to the network. Then we're going to talk a bit more information, how we encapsulate and how we decapsulate all this information, as well as the size, message size. We have to agree on the message size. We can't, for example, send the website, for example, we can't send the whole website at one go. We have to break that message, that website, or into small messages. And it's important that we agree on how big are these messages, or how much of these messages we can send. For example, imagine that's a website. Yeah, that's a website that we want to send. All this website is we're gonna be breaking into small pieces, and each piece we're gonna send it. And then we're gonna be talking about what are these pieces called, like segments and so on. Then we talk about message timing. Message timing. So message timing, we have to have, for example, the access method. Access method. For example, who will be able to send at what time? If two devices that send at the same time, there's going to be a collision. And if there's a collision, we have to wait, and then we start the process again. We listen to the wire, make sure that nobody else is sending. If nobody else is sending, then we will start sending. So like we said, if two devices send at the same time, there's going to be a collision. So we have to control that. As well as we have to control flow control. Flow control. All this is under message timing. So how much data can I send to you? For example, I can't send all the packets, like just bombard you with lots of packets, and then you're going to say, oh, I can't accept all these packets, and the message is not going to get to the destination. So in the network communication, source and destination host use this flow control method to negotiate correct timing for successful communication. And then response timeout. So we talk about the response timeout. So for example, if me and you, we are chatting, we need to know, well, who's going to talk, right? You kind of agree that, okay, you talk, I listen, then I'll talk, and then you listen, and so on. And then while we are talking, we're going to have a pauses, right? So I can't just say all the words very quickly. I have to have the pauses so you can understand all the messages, as well as we have a response timeout. So I say kind of like nodding, like, yep, I understand that, whatever you're talking. Same with the PCs, they have this response timeout saying that, okay, I'll send you these 10 segments, and then I'll wait for you to acknowledge that you got those 10 segments. If you didn't, then I'll act on that. For example, I'll send you another 10 segments, or I'll send you these 10 old segments that you didn't get them back. Or if you acknowledge, they say, yep, I got them, I'll send you the next 10 segments. And then message delivery options. We have, for example, one-to-one delivery. For example, we have a one PC communicating to another PC. That is one-to-one. One-to-one. One-to-one is another name for it. We call it as unicast. So this is a unicast communication. Another type of message is when you send in to a group, not to everybody. Just imagine that this PC's got connection to 3 PCs here, and PC 1, 2, they're communicating with each other, and we have PC 3. So when we send a message to a group, a message, that is called one-to-many. So one-to-many, not to all, to many. And that is a multicast. So we have a unicast, one-to-one. We have a multicast, one-to-many. The source is always going to be a single host. So that's always going to be the source. This is never going to be the source. A group will never be a source. The group will always be the destination. And the last one is if we send to all. So if this PC is sending a message to all the other PCs, that's called a broadcast. So broadcast. Or one-to-all. 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 That's the broadcast, if you're communicating with everybody. Broadcast, again, cannot be a source. We can't have a source as a broadcast. The broadcast will always be the destination. Protocol suites and industry standards. Now we have a different protocol suites: TCP, IP, ISO, AppleTalk, Novel NetWare, and so on. But all of these don't need to learn. On this curriculum, we don't need to learn, and pretty much everything is TCP IP model. Now we have a layers. For example, this is the application layer, this is a transport layer, internet layer, and network access. As you can see, the network access is the same for all different standards. But the only one that you need to learn is the TCP IP model. And then we're going to be talking a bit more in depth later on about these protocols that work on each layer, like application layer protocol, transport layer protocol, as well as the internet layer protocol, as well as the Ethernet. PPP, I don't think is covered on the CCNA cybersecurity. CCNA routing and switching, definitely. So we have to learn in depth the TCP IP protocol. As a CCNA cybersecurity or CCNA routing and switching technician, you really need to know the TCP IP protocol suite. Now, where did it come from? It came from, for example, Advanced Research Project Agency Network, ARPANET. So all this is from ARPANET. Now, what the ARPANET, who was made? And ARPANET was made in 1969 by a Department of Defense, United States Army. 4 networks, they wanted to communicate with each other, even if one of them failed and so on. So this is what we have. We have in the TCP IP protocol, we have application layer protocols. Like, for example, in application layer protocols, which we're going to be talking about in more depth later on. But DNS, it resolves a name to an IP address, because we as humans, we don't remember IPs or numbers as well as we remember names. So DNS will be resolving that. Then we have a DHCP. DHCP, it assigns IP addresses to client computers, for example, or leases IP addresses to clients. So we don't have to go, we can do that. We can manually give an IP address to every computer, but yeah, it's time consuming. So we leave it to the DHCP protocol to do that for us. And then we have a SMTP. SMTP is email, sending email. So sending emails, and these are for receiving or downloading emails. POP3 and IMAP is for downloading emails. And we'll see what's the difference between them two. IMAP is synchronization, while POP3 downloads the email. Then we have a file transfer protocol, so FTP and then TFTP as well. So reliable and the best effort delivery. And then we have a web browsing, HTTP, for example, or HTTPS. Then we move on to transport layer protocol. Transport layer protocols, I'm going in very fast in this because there's going to be a slides explanation about each protocols in more depth. A UDP is a best effort delivery, while TCP is reliable delivery. And then we have an internet layer protocol like IP, NAT, network address translation. This is for verification, ICMP, and control. Then we have a routing protocols, which we learned in routing and switching, OSPF and EIGRP. And we have a network access layer protocols. This doesn't matter if it's TCP, IP, IPX, AppleTalk, they're all the same. In there we have ARP, point-to-point, Ethernet, and interface drivers. Communication protocols. Another model that we can talk about is the OSI model, or called Open System Interconnection OSI model. This model has 7 layers, a bit more in depth than TCP/IP model, which had only 4 layers. In the networking, when we communicate and we're saying, okay, layer 4 problem, we are really referring to OSI layers, or layer 6 problem, or layer 2 problem. We really referring to the OSI. In there we have we have 7 layers, which we're gonna go in depth in all these layers. For example, application layer. In there is like we communicate as a user. We are here in the top of it. When we open a browser, or when we click on the hyperlink, or we do something, we interact with application layer, layer 7, which will define what did you do. What application did you use to access this? For example, is it web application? Is it email application? That's what they know, application layer protocols. And then they kind of encapsulate to that protocol that you're using and move the data downwards this way. And as soon as it's going downwards, that's called encapsulation. So we are encapsulating, let me just write encapsulation. So it's moving down. Presentation looks at that data and says, okay, what do I do? How do I format it? So presentation layer, it deals with formatting only. Well, not only, but major thing. Format, and as well as encryption. So what do I need to encrypt this data? And after that, the presentation layer, it moves it downwards and goes to the session layer. Session layer deals with communication, idle. It's called the management of the communication. And then the fun bit starts at the transfer layer. These 3 top layers, all the data is just data, big piece of data. Now, when it gets to the transfer layer, it takes that data and it makes it splits it into small pieces, right? So it splits that data into small pieces. Each piece is called a segment, so segments, and then it moves it on. So each segment is got a sequence number. If it's reliable, it's got a sequence number for reassembling. So for example, we took that data, we put it into small pieces, and we forward the pieces. Well, later on, they're going to be forwarded the pieces to the destination. Destination should be able to reassemble the way they were broken down to small pieces, and they will use those segments for that. In here, the transport layer communicates with the application layer, because the 3 layers on the top is just called data. And transport layer looks at the application layer and says, okay, well, what is it? If it's HTTP, it will put, for example, port number. So it will identify ports. For example, it will have a source port number, source port, as well as the destination port number. And here at this layer, it's called a segment. So because it takes it and it segments it into small pieces. That's an MTU size. And then after the transport layer gives it to the network layer. Network layer adds an IP addresses. Each segment will put, that's a segment. Network layer will put a header on it, and in that header we'll put an IP address. So we have a segment and say that's the data. So we have a data segment, then the network layer will add a header. That's called a packet now. And when it reaches this layer, it's called a packet. And a packet puts a source IP address and destination IP address here. As far as the network layer is concerned, it doesn't really understand what's inside here. It doesn't really care. It just says, okay, well, I can identify what is it. Is it TCP, UDP, or what kind of protocol is DNS, DHCP, or whatever. But it doesn't really concern what's inside it. It puts the IP address. So now when it moves it down to the data link layer again, even though there is stuff on it, there is other headers. So there's an IP header here, there's a segment header here, so packet, segment, and there's data. But the data link layer really doesn't really care what's inside. It just sees it as data. So all this is data. And the data link layer adds a header. And in that header is going to be source MAC address and destination MAC address, one of the fields. Yeah, you're gonna learn a bit later more inside what's in those fields. And when you get to this point, it's called a frame. So here we call it as a frame. After it adds a header, it adds a trailer as well. That's a frame check sequence, making sure that there's not any errors on that frame. It hasn't been corrupted. And then when we move it to the physical layer here, physical layer, we just call it a bits. So we put them in zeros and ones. Well, the network layer, the communication protocol puts it on zeros and ones, and it moves it down to the either fiber optic, wireless, or copper. Okay. Sorry for all the scribbling. I hope you're understanding. So 3 addresses that we talk about: protocol addresses. That on the segments, we look at the address, the protocol address, the network host address, and then the physical address. So if you remember, in here they were called the segments. In here they're called packets, and in that layer they're called frames. And here just bits, zeros and ones. If you want to say that you don't want to discuss frames, packets, segments, at any layer, this is called PDU, protocol data unit, right? Protocol data unit. If you don't want to say, for example, there's no another name in presentation layer, but if you want to say, okay, well, at the presentation layer, this protocol data unit was doing this, and so on. Thank you very much for watching this section, 4.1 protocols. Please have a look at the other videos. And don't forget to subscribe. This has been Astro Krasniqi. Next video, 4.2 Ethernet and Internet Protocol. Bye bye.